Okay, welcome back. We're in the final unit of this course. We have talked about many different topics. The goal of Unit 5 is to put it all together in a way that we can describe the operation of virtually any semiconductor device using these concepts that we've been discussing throughout the course. And the subject of this lecture is just a mathematical formulation of this set of equations that describes the performance of semiconductor devices. Okay, so we have talked about solving semiconductor problems, and we've solved many problems. We've talked earlier that if we have a uniform semiconductor in equilibrium, then it's reasonable to assume that the mobile electrons and holes flow around in a way that neutralizes net charges, so that we can assume that the net charge density is 0. And we also know that in equilibrium, N times P is Ni squared, a material and temperature dependent quantity. And putting those two together, we can solve for the electron and hole concentrations in a semiconductor device in equilibrium. But in general, these equations won't be valid. We may be out of equilibrium. So how do we solve for the electron and hole concentrations out of equilibrium? And we'll see that we're going to need to solve for the electric field as well. Well, just to refresh your memory, these are our equilibrium conditions. This is our relation between the equilibrium electron concentration and the Fermi level and the intrinsic level. This is for the hole concentration. Here's our NP equal to Ni squared relation. And we know that the probability that a state is occupied in equilibrium is given by this Fermi function. The two key parameters are the Fermi energy and the temperature. Okay, out of equilibrium, something similar happens. There's a relation between the carrier density, but now not the Fermi energy, and the quasi-Fermi energy. So we need to find the quasi-Fermi energy out of equilibrium, or alternatively, just find the carrier density. There's a relation between the hole concentration and the quasi-Fermi level for holes. So the subscript 0 over here refers to equilibrium. No subscripts here refer to the fact that these equations apply out of equilibrium. Out of equilibrium, NP no longer equals Ni squared. So you need to be careful. Never use NP, or almost never use NP equal to Ni squared out of equilibrium. What is NP out of equilibrium? Just multiply these two expressions together. You can see it depends on the quasi-Fermi levels. And finally, the probability that a state in the conduction band is occupied is not given by the Fermi function out of equilibrium. It's given by something that looks like a Fermi function, but instead of the Fermi energy, we have this quasi-Fermi level that describes the occupation of the conduction band, so the electron quasi-Fermi level. And for the valence band, we're interested in the probability that a state is empty. That's 1 minus F. But F is not given by the Fermi function. It's given by something like a Fermi function, but instead of the Fermi level, we have the quasi-Fermi level for holes. So this is the formulation. We're looking for how do we solve for these carrier densities, or equivalently, how do we solve for these quasi-Fermi potentials out of equilibrium. So our unknowns are the carrier concentrations. The carrier concentrations are related to the quasi-Fermi levels and to the intrinsic level. The intrinsic level, or the conduction band, or the valence band, they're equal to some reference energy. Anytime we have an energy, we have to define a reference. But then there's an electrostatic potential due to the electric fields that are set up by these charged particles that moves these bands up and down. So we need to know how the intrinsic level varies with position in order to relate the carrier density to the quasi-Fermi potentials. So there are three unknowns here. There are either the two carrier densities and the voltage, the gradient of the voltage gives us the electric field, or completely equivalently, we could say that the three unknowns are the two quasi-Fermi levels and the electrostatic potential. We need three equations and three unknowns. Those three equations will give us the mathematical description of a semiconductor, any semiconductor in which the simplifying assumptions are valid. So let's talk about the first equation. The first equation is an equation for the hole density. There'll be one just like this for the electron density. And we call it a continuity equation. And the way I like to think about it is like this. Let's assume that I have a lake that has some water level, and I would like to write an equation for the water level. I'm going to call this water level P, because it's like a hole concentration or number of holes. So I'm going to ask, what is the rate of change of the level in this lake? Well, if I've got a stream that's flowing into the lake, there's some inflow that's increasing the level in the lake. But if the stream flows out the other side, there's some outflow that lowers the level. Okay, so those two processes are going to, the net, if inflow is greater than outflow, the level will increase. Now, I could also have generation processes. Rain would increase the level of this lake. That's a type of generation process, and we discussed generation processes for semiconductors. I could also have recombination processes. Recombination processes in this example would be like evaporation, which would lower the level of the lake. And we discussed recombination processes for semiconductors. So we can just write a bookkeeping equation that accounts for all of these processes. We can say the rate of increase is equal to the net flow in plus the generation rate minus the recombination rate. We would call this a continuity equation for holes. And we would write it this way. dp dt. Remember from your vector calculus that divergence of a vector we interpret physically as a flow out. The flow here, inflow and outflow, is related to the current of holes. So the current divided by Q is a flux. That's the flow in or the flow out. Divergence of that flux physically represents a net flow out. Minus divergence represents a net flow in. And then this is the generation process for holes and the recombination process for holes. So this is the first of our three equations. And it's a bookkeeping equation. The holes can't magically appear from anywhere. We have to account if the hole concentration is increasing with time at some location in a semiconductor. It's increasing with time for a reason, and these are the three reasons here. There is a similar equation for electrons, and that's the second equation. Okay, so let's look at this hole continuity equation. This is the first of our equations. We're going to need the whole current, but the whole current, we already have an equation for that. It's related to the electric field and to the hole density and to its gradient. All right. So there's a new unknown here, the electric field. So we're going to need to formulate an equation for the electric field or for the electrostatic potential. Remember, the gradient of the electrostatic potential minus the gradient is the electric field. So we need another equation. This is our explicit generation term. It might be the generation of holes due to light or impact ionization. And R is our recombination term. And remember, we have discussed three different recombination processes. Remember that there was a term NP minus NI squared in all of those processes. Recombination was always proportional to the product of the number of electrons times the number of holes. So even to solve for the whole continuity equation, we need an equation for the electrons. Well, that's just an electron continuity equation. So the one to focus on is this additional equation that we need for the electric field. And to do that, we'll go back to electrostatics. You have probably seen Gauss's law in a freshman physics course. And the way you thought about it was probably like this. If I've got a charge enclosed in a spherical volume, we'll call that a Gaussian surface. There will be a normal vector that points away from that surface. I'll label that N. And we know that there will be an electric field that will emerge from that charge. There will be a displacement field that is the permittivity of free space, epsilon naught, times that electric field. In a semiconductor, not in a vacuum, we will have the material will respond and polarize, and the permittivity of free space needs to be replaced by the relative dielectric constant of the semiconductor times epsilon sub naught. This can be quite substantial. It's on the order of 10 or more in common semiconductors. Okay. And Gauss's law says that if we do an integral of the displacement field dotted with a surface area which is pointing in the direction of the normal, if we do a closed integral and enclose all of that charge, the integral of d dot ds over that surface will equal to the charge enclosed. That's our statement of Gauss's law. Okay. We can see it more easily in one dimension. So let's assume that I have a large cross-sectional plate of area A coming out of the screen here. I have another one located at x plus dx on the other side. We have an area A. Now, the normal vector on this surface will point out in the same direction that D is pointing. The normal to this surface is pointing in the minus x direction, in the opposite direction that D is pointing. So if I do this integral, I have to integrate over the face on the left. I have a minus sign because the normal and D are pointing in the opposite directions. I also have to integrate over the plate on the right. There's a positive sign there because the normal and D are pointing in the same direction. And if I do those two integrals, remember these sheets are extending infinitely in the other two dimensions, so the only places that D can emerge are from these two surfaces. So this is my integral over the surface, and that integral has to be the charge enclosed. Okay. Well, the charge enclosed, I'm going to write if the material inside has some space charge density in coulombs per cubic centimeter. I will multiply by the volume. The volume is simply the area of these faces times the thickness of this region, A dx, times the space charge density. That gives me the total charge in coulombs. And then I can rearrange this equation. The displacement vector at x plus dx minus the displacement vector at x divided by dx, I'll divide through by dx, is equal to the space charge density. Okay. So when I do that, I recognize a derivative. This says dd dx is equal to rho. I have a simple equation for the displacement field, and since the displacement field is dielectric constant times electric field, I have a simple equation for the electric field, and that's what I'm after, my third equation. In 3 dimensions, it would work like this. Integral of d dot ds is equal to charge enclosed. That's the initial way we stated Gauss's law. And an equivalent way, a differential form of that equation, is divergence d is equal to the charge density rho. That's our third equation. D is related to the electric field, so that will give us the electric field. So our third equation would be divergence, relative dielectric constant, times epsilon naught times electric field is equal to the space charge density. Okay, well now we've got another unknown, the space charge density, but actually we don't. Because we remember the space charge density is charge times the mobile hole concentration. We have an equation for that. That's the hole continuity equation. Minus the mobile electron concentration. We have an equation for that. It's the electron continuity equation. And then the ionized donors and the ionized acceptors, and presumably we know how we've doped the semiconductor, so those are not unknowns, those are known. So we've got our third equation, and we can put this all together. These are sometimes called the semiconductor equations because they're often taken as the fundamental description of any semiconductor device. We have a continuity equation for holes, we have a continuity equation for electrons, and then we have the Poisson equation, which tells us the electric field that results from these positive and negatively charged carriers, the positively and negatively charged donors and acceptors, and the third equation tells us the electric field that results from the motion of those mobile carriers. So we have 3 equations for 3 unknowns. Remember, this V is the electrostatic potential minus its gradient is the electric field. We have these constituent relations for the electron, for the hole current, for the electron current, and for the space charge density, and the electric field is minus gradient of that potential. So these are 3 equations and 3 unknowns. If we simply solve these for a semiconductor device, we can understand the operation of the semiconductor device. Now, I'll point out that these equations are, they're not as fundamental as Maxwell's equations. We made some approximations. They work remarkably well for many semiconductor devices. They're usually our starting point when we encounter a new device. The continuity equation is a bookkeeping equation. That has to be right. But the current equations, we've made assumptions. We made assumptions like low electric fields, and we've ignored complexities due to hot carriers and some transient effects and things like that. We also have no time dependence in the third equation, so we don't have electromagnetic waves. So we're considering semiconductors under conditions in which currents and electric fields are not varying too rapidly in time. But this is generally the place that people start. When you encounter a new semiconductor device, these are the equations that we need to solve. They're relatively complicated. These are three coupled partial differential equations. They're nonlinear. So their solution is not completely trivial. It takes some skill and thought and understanding of the physics underlying them in order to simplify them appropriately and understand the operation of devices. But that's what understanding devices is all about. Now, we also have today powerful computer simulation techniques that will simply give you the numerical solutions to these equations. Those are commonly used. If you work in semiconductors, you want to be familiar with using these computer-aided design tools. But you want a deeper understanding of how these can be simplified under specific conditions that will allow you to understand the results that are coming out of these computer simulations. Now, those are complicated equations. What happens in equilibrium? In equilibrium, those equations simplify considerably. Nothing changes with time in equilibrium, so there are no time derivatives. No currents flow in equilibrium, so there are no currents. There can be no net recombination or generation. So everything simplifies considerably. You can actually, we could have electric fields in equilibrium. That's okay. But you can actually show, and I won't go through it here, that you can solve these equations in equilibrium, and the solutions to those equations would be solutions that we've seen before. So the equilibrium solution to this complicated set of equations is consistent with our earlier expression of equilibrium carrier densities in terms of Fermi level and with the fact that NP is equal to Ni squared. And just to remind you, when we write recombination or generation and recombination this way, by R, I'm meaning, the processes such as band-to-band, defect-assisted Shockley-Reed-Hall, and Auger processes. If R is negative, these actually become generation processes. I've simply chosen then to explicitly label the generation processes as things that are explicit, like generation of carriers optically. So just a matter of notation there. Okay, now let's take a look, thinking about generation and recombination in equilibrium allows us to go back and explain something that maybe had been a little mysterious earlier on. So a generation process will take an electron from the valence band and move it to the conduction band. And that could be any one of a number of different processes. The inverse of Shockley-Reed-Hall, for example. I'll just call that little g. Okay, requires some energy to do that, to break the covalent bonds. A recombination process will take an electron from the conduction band and remove a hole in the valence band. I'll call that little r, and that could be any one of a number of processes. Right? And that'll release the energy. Okay, now in equilibrium, these two have to be in balance because nothing is changing in equilibrium. There will be thermal energy that can break bonds and create electron-hole pairs, but then those electron-hole pairs will recombine and the two will balance in thermal equilibrium so that on average everything stays the same. So in thermal equilibrium, the net recombination rate, R minus G, has to equal 0. R has to equal G. Okay. Well, this simple fact can help us understand why NP is equal to Ni squared, a material and temperature-dependent parameter in equilibrium. So in equilibrium, there is some thermal energy that can break the covalent bonds and create electron-hole pairs. So this generation rate is described by some temperature-dependent function, it is also a temperature and material dependent function because it depends on the band gap of the semiconductor. The wider the band gap, the harder it is to create these electron-hole pairs. So there is some function G that describes this generation process in equilibrium. Now there's also a recombination process, and for an electron and a hole to recombine, an electron has to find a hole, so it has to be proportional to the product of the electron concentration and the hole concentration. And there will be some material-dependent parameter here that will describe the strength of this process, whether it's a direct band-to-band recombination process or a defect-assisted process or whatever it is. Now, when we say that in equilibrium, these two processes have to balance so that nothing changes with time in equilibrium, we say G is equal to R. If I simply equate these two and solve for NP, you'll see that NP is some material and temperature-dependent function that describes the generation process, divided by some material-dependent function that describes the recombination process. So the product of N and P is some material and temperature-dependent parameter. This is what we call the intrinsic carrier concentration squared. So it's really this balance of generation and recombination in equilibrium that explains why NP is equal to Ni squared in equilibrium. Okay, so just to wrap up, we have mathematically formulated the semiconductor problem in this unit. We have three equations in three unknowns. The three unknowns are the hole concentration, the electron concentration, and the electrostatic potential. We have a continuity equation for holes, that's the first equation. We have a continuity equation for electrons, that's our second equation. And we have the Poisson equation, which gives us the electric field. We have these constitutive relations. We know how to express the hole current and the electron current in terms of the hole densities and the electron densities and the electric fields. And we know how to express the space charge density in terms of the mobile carrier densities and the doping of the semiconductor. And we get the electric field, we relate that to minus the gradient of the electrostatic potential. So these are actually three quite complicated coupled partial differential equations that are nonlinear. If we solve these equations, we can understand the operation of any semiconductor device. There are powerful computer techniques now and computer-aided design programs that numerically solve these equations and will give you the answer. But in order to understand the operation of devices, we really need to understand how one simplifies these equations for the device of interest and then understands how the device is operating. That will help us understand the results that sophisticated computer simulation programs give us. Now, before we talk about actually solving equations like this, in the next lecture, we'll talk about a very powerful qualitative way that will provide us with insightful qualitative solutions to these equations without doing any mathematics whatsoever. That's the subject of the next lecture.